Welcome to
Thanks, you, Dan.
Walkabout the Galaxy, the 300 episode astronomy podcast where the science is universal, the opinions are personal, and the hosts are reunited.
And it feels so good.
We are Strange Charm Up Top and Original Top, the Astroquarks, also known as Josh Caldwell,
Addie Dove.
Hannah Sargent.
Jim Cooney.
And Tracy Becker.
coming to you from distributed locations to your distributed location. It's a delight to welcome back to Walkabout Dr. Tracy Becker, who originated Top Astroquark. Tracy, how does it feel to step back into the role that you created of Top Quark?
It feels incredible. I'm very excited to be here. I'm excited for the 300th episode as my reintroduction to the podcast, too. So that's fantastic.
I think it's kind of like the Friends reunion episode. It has that same kind of vibe. You know, just get back into the set and it just, everything is clicking, all that original Astroquark magic.
Yeah.
And we all look wildly older than we did when we were still.
Hey.
I was going to say, does anyone look crazy sick or Chandler wasn't doing so well during that Friends reunion?
Jim and I may look wildly older. The rest of you, I think, look nicely older or
well-aged,
more mature. Any risk of annihilation between you and the other Top Quark here?
I think the separation between Florida and Texas is going to keep us safe.
Okay, sounds good. Well, since this is our 300th episode, I had to do something with 300. Our stumper today is 300/fantastical. So if you may remember the movie 300, the heroes face an invasion of soldiers and fantastical creatures representing the Persian army led by a sort of superhuman god king Xerxes with all sorts of wild, fantastical, monsterish creatures. Helping raise support for our heroes back in Sparta is Queen Gorgo, played by Lena Headey.
Oh, nice.
And Lena Headey played another queen in another fantastical show, Game of Thrones, where there was also a horde of fantastical invading creatures, the White Walkers. So your stumper is Game of Thrones invading bad monsters or 300 invading bad monsters. Jim.
Well, you know what? I guess I'm a bad fantasy lover. I am a lover of fantasy and Tolkien and all those kinds of things, but I have never gotten into, I've never read, I've never watched Game of Thrones. So I have to go with 300, which I think is a really neat, awesome movie, and I enjoyed the heck out of those fantastical monsters.
All righty. Original Top, what do you say?
Game of Thrones, especially because it was the season finale last night of House of Dragons.
Oh,
okay.
It sure was.
So you're going with the White Walkers. Hannah, do you remember either of these shows, or have you seen them, movie and show?
I don't really remember 300, and I haven't seen Game of Thrones. So, I mean, I'm just following the general. I need to live up to my name of knowing nothing about,
being the least nerdiest person on the show.
Yeah, pop culture fantasy is not my forte.
Yeah.
But what was the question? What I'm more afraid of?
No, it's just
what would I rather?
Just one or the other. You get to choose what.
300 because I've seen it once.
There you go. Okay, Addie, what do you say?
I'm going to go with Game of Thrones because I do think a lot of the different invading hordes in that were pretty good. And I honestly didn't remember that there were monsters in 300.
Really? Okay. I'm going to
go. I think I was entirely with it when I watched that movie.
Oh, okay. Interesting. That sounds like something for the, behind the scenes of Walkabout the Galaxy. I'm going to go with 300. Kind of I watched some of Game of Thrones, just never really clicked for me.
Now I feel like I need to watch 300 again, though. Maybe we'll do a Astroquarks Watch 300.
There you go. Well, today we'll talk about ancient astronomy, black holes, Europa, and much more. But first, this episode of Walkabout the Galaxy is brought to you by Quasars. Supercharge your galaxy with a quasar. Quasars are not your parents' quasi-stellar radio sources. emitting light across the entire electromagnetic spectrum with a power up to 1,000 times greater than the entire output of the Milky Way galaxy. A quasar is just what you need to put some pep back into your galaxy. With a simple fuel source of gas and dust and an accretion disk around a supermassive black hole, you can keep your quasar blazing for hundreds of millions of years, and you can recharge it by arranging for a collision with another galaxy, converting gravitational potential energy into intensely bright radiation. Since the universe was less than 1 billion years old, quasars are your tried and tested sources for every color of the rainbow and more. Quasars, where clean energy lives.
Should we be
Ooh.
worried that 300 episodes in and we've never had a repeat sponsor?
I was shocked when I found that Quasars had not sponsored an episode, when we have had sponsors from some particularly odd and unexpected entities.
We really
Niche,
Uh,
Josh,
have
niche.
a list of that, yeah.
Some niche sponsors.
Yeah.
Thanks
Thanks to Quasars for reaching out this time.
Quasars, a pillar of
Yeah.
cosmology, and it took them. They wanted to wait for this special episode, the 300th episode, where clean energy
honestly,
lives.
they probably felt like they were getting enough coverage anyway, right? We do talk about them a lot, so they probably felt like they didn't even need to advertise. We were advertising for them.
That's true. Fair point. Free advertising. Exxon.
Clean?
That's why I'm laughing.
Hannah, what do you think?
I can't name any clean energy suppliers, so I'm out.
Yeah,
Just make something
Jim.
up. Make up BP.
Clean Energy Corp.
The Clean Energy Corp. Okay. Tracy, any 3 Mile Island. I love the cynicism of these guesses. Well, you all obviously had the right general idea. It is an energy company. It's Con Ed, Consolidated Edison.
I don't think I know what that is.
That's an electric company.
Checks out.
Yep. There was some new JWST images that you wanted to report on before we jump into our overview of everything from ancient astronomy to future astronomy.
Yeah, there's a new addition to the JWST hallway corridor, and I feel like we switch back and forth every time.
I do.
And
we do.
It's a beautiful display they've added of the pillars of creation.
Which was already beautiful from Hubble, right? It was already incredible.
This is kind of like it's kind of like the Carina Nebula one, where it was like already the spectacular images, and they redid it with JWST, and it's beautiful.
Which is better?
Carina.
Which is better, JWS?
I honestly
like the Hubble one.
The Hubble picture is prettier, but it's different. You know, in the JWST one, you can really see the places where the new baby stars are being born because they give off a lot of infrared light. You can see them really clearly. Whereas in the Hubble, they just tell you this is where baby stars are being born without really seeing them. But
yeah,
it's a little bit more transparent, right, in the JWST image.
It is. It is.
So it's partly because you're in some sense seeing through the pillars of creation a little bit more than you are in the Hubble image because the longer wavelengths that they're looking at there.
Yeah, because the gas in those pillars is cool, right? And so the gas and dust are cooler there, and so yeah, they're more transparent in the IR.
We have ancient astronomy to future astronomy. Tracy, we've bragged about you a lot as being on the Europa Clipper mission, which is very exciting, and that's our future astronomy, which we will get to a little bit later. We'll start with some older astronomy, and there was an interesting story about, I don't know if ancient astronomy is the right term or not, but sort of before what we consider our sort of,
I think it's ancient
Renaissance
astronomy.
revival of astronomy.
Yeah, so basically, in terms of the ancient astronomy and creating star maps or like recording the locations of stars in the sky, it's kind of been known, I say that with like air brackets, that
and by air brackets she means air quotes.
Yeah, those things. We can do brackets. That's fine.
Could be a bracket.
The British translation.
Yeah, that's definitely how we do it. It's been known that Hipparchus created or recorded the original star map because he's been quoted as doing that, or those maps have been quoted, but the actual original text has never been discovered. So it hasn't been like proven necessarily that it was him that has the oldest star map. The only proven one that we've seen is from Ptolemy, which was a few hundred years later. But there's a team of researchers that have discovered some recordings of star locations on ancient, basically ancient paper. And because paper was harder to come by back in the day, they often used to scrape away text on the paper to then reuse it and write new things on top. And so they've been analyzing these different sheets of paper and trying to use these really cool techniques to try and see deeper within it and see what was there before. And they've discovered some locations of stars that could only have been the location of those stars at that time basically matches what it would have been during Hipparchus's time. It was also recorded in the way that Hipparchus tended to write things. And so they think they found the original star map. And go on.
No, you go. Sorry.
I was going to say, and what's quite cool about it is that it's more accurate than Ptolemy's star maps, which were a few hundred years later. So it's generating quite a bit of excitement, but it's only just a few locations of stars, and they think there must be a lot more written on other pieces of paper. So they need to do a lot more analysis of these documents. Yeah.
So Hipparchus lived in the 2nd century BCE, and Ptolemy was so from like 162 to 127 BCE was his sort of working astronomical time frame. So 2,200 years ago, give or take, something like that. So are you saying when you said that like the star positions had to like be from him? Is there?
Yeah.
What do you mean? What exactly do you mean by that?
So they've dated the paper to a certain like range of like span of time, and then within that, I guess like the wobble of the Earth has like it causes like this slight shift in like location of stars to us, and that I think that goes every like 70 odd years or so, that wobble. And so within the time frame of the age of the paper and the wobble of the Earth, they've taken the locations of the stars that have been recorded and isolated it to a time and figured out what the wobble was and therefore what the year was that he must have.
How did they figure out the position of stars in the sky without turning back the sky with the ancient god, like in Moon Knight? The only way you can do that is by physically turning back the sky to figure it out. Sorry, that's right. One of my least favorite
use any software to do that.
No. Yes, I'm so glad I got to recycle that rant.
Yes, you can't use like a $5 app on your iPhone to figure out what the sky looked like back then. So
this is this thing they do with like multispectral imaging, and they're starting to do this with all these ancient texts, and it's super cool. And it's just crazy how we're like digging out all this ancient information and like, where is this other stuff? Was it on some other? It's going to be in some other random book somewhere, right? They're probably not even like together anymore.
I thought this was really cool, and one of the cool things is there's a word for that thing, for like a piece of parchment that has been erased, written over. there's a word. It's like palimpsest.
Palimpsest. Yeah.
That's great.
Is that a Scrabble word, Jim?
It's too long for a Scrabble word, but it's a cool word. I'll say that. That whole thing was really awesome. It's amazing what they can figure out these days with all that stuff.
And what I really liked as well was that this kind of came about from a student summer project. So someone at the University of Cambridge, a biblical scholar, issued these different pages to some students and asked them to just take a look and see what you can find. And then was like, wait a second, this is awesome. Really important.
That's awesome.
Yeah.
Because there's like thousands and thousands of these things out there, and the technology is brand new. So it's like there's projects for a zillion students.
A gold mine
now. Yeah.
Really awesome. I wonder
Yeah,
how well they're going to be able to like scan some of these and start to do like citizen science type projects where they have like the different
Ooh,
images scanned and they can start to do some citizen science versions of it where you're
love that.
crowdsourcing it.
so Hipparchus did many things, and one of which was basically discovering the precession, this wobble of the Earth. So you mentioned a 70-year period. There's a 26,000-year period for the full cycle of the Earth's rotation axis around the celestial sphere, but there's these shorter period oscillations on top of that. But he discovered that precession, which we sort of observationally think of as a change in the position of the equinox on the celestial sphere. So he discovered that among many other things. So it's very cool to go back. I love that ancient astronomy stuff too. Like that recently, one of my favorite stories was about Betelgeuse and these ancient
Yeah.
texts and showing how its color has changed just in the last couple of thousand
Yeah, that
years.
was a fun one.
Yeah. Speaking of Betelgeuse, whose color was compared not to Mars, but
But
to
to Venus.
Saturn
Oh,
and or Venus. I thought anyway, but they're both yellow, so it's
they're both
fine.
yellow.
But that's where I was going, Addie. I was
Yeah.
heading towards Venus.
Yeah. One of the things we've talked about a few times off and on recently, over the last few years, has been this phosphine on Venus debate. So there was a discovery, I'm also using air brackets, in 2020 of phosphine that's been highly contested, and we had our own expert on the show to talk about it, I think, when it was originally discovered. But there's potentially some newer results that have come out. So they've done 3 observation campaigns now of Venus, and they use radio wavelengths to look for the signature of phosphine. So phosphine is like ammonia is NH3 and phosphine is like pH3, I think, right? So it's
Yes.
this molecule that you can look for, and it's created by a lot of like industrial processes here on Earth, but it can also be created by like anaerobic organisms. So maybe it's a sign of life, because like how much there is, you can't just have it would go away in the atmosphere. So maybe it's a sign of life in the upper atmosphere of Venus. And so they're tripling down apparently on this detection. Although
They're
almost
tripling
everyone
down
else,
on it.
I think that's I think the paper hasn't come out yet, but there's been some interviews and a few other things where the folks who are researching this and have the data are tripling down on the fact that they think that they see it. And so I'm sure there will be another round of rebuttals once the new paper comes out. But it's just like, it seems it's very hard to have it be phosphine and like something produced by life, right? Like there's a lot of other explanations, and one of the big challenges of like the wavelengths that they're looking at is they're like right next to or basically the same wavelength as like other potential signals,
Right.
and these observations are coming from the Earth, so you have to take into account the Earth's atmosphere when you're doing this. So there's a lot of challenges to these observations. It would be nice too if there was like some other complementary signal, right, that would tell us that this is happening and it's not just this like one phosphine signature.
Can we just go there and scoop up some Venus atmosphere and check it out?
Yes.
I think, aren't there 3 missions planned to go to Venus in the next couple of years? So maybe
Yes.
we'll solve this with some of those missions.
Yeah, I was wondering about that, and I don't know if I'm sure somebody somewhere it's been commented on, but like if the phosphine signature would be able to be seen in any of the wavelengths or any of the detectors that are being sent. I'm not sure.
So talking about like going back and looking at old data. So the initial, as you mentioned, discovery, air brackets, discovery of phosphine in 2020 prompted people to like go back and look at their old observations of Venus. And so apparently one of the older sets of data that were reanalyzed were from Pioneer Venus, a orbiter of Venus, which had detected things you mentioned, that like the spectra, there's all sorts of things in various regions. So a reinterpretation suggested that some of the detections of Pioneer Venus, which had said, well, we fit this with chlorine and hydrogen sulfide, Now they're like, well, if there's phosphine there, actually we get a fit with phosphine instead of those other
Oh,
things. But then also an analysis of measurements from the NASA IRTF ground-based
infrared.
facility from 2015, didn't reveal any phosphine, and they were able to place an upper limit that's like 5 times lower than the detection from
Oh,
September
yeah.
2020. Now, as you said, they've tripled down, so there are these other more
Are they
recent
looking in like
measurements.
different parts of the atmosphere at all? Or I don't know.
Different parts of Venus's atmosphere.
Yeah.
I don't think that's possible really with JCMT. I actually accompanied one of our guests who discussed this with us, Brad Sander, to some
Yeah.
observations of Venus with JCMT, and it's a couple of pixels.
Yeah.
Venus is so
Okay.
you can't really say much
Sure.
that way.
Cool.
Let the planet rotate, but. So that's interesting. So we're still waiting for the new papers to come out. Maybe we'll have to wait for Da Vinci Plus or these other missions that are in the works for Venus to get a definitive answer. And then if we get the definitive answer about phosphine, it's like, what the heck is producing it?
Yeah.
And keeping it there.
Will we have more questions then? Or
yeah. Well, before we jump out from Earth and Venus to Europa and beyond, I'll drop the trivia on you, which is inspired by our sponsor. It's Quasar Trivia.
All right.
So, quasar activity seems to have peaked about 10 billion years ago and declined as the material that feeds the quasars around the supermassive black holes was depleted, so that there's not as much stuff falling into these accretion disks, not as much energy being produced. So that the era of quasars was kind of a while back, which also means they're mostly far away. So the first question is, what is the distance to the nearest known quasar in light years? So how many light years to the nearest known quasar? And your piece of context information is that the heyday of quasars was 10 billion years ago. And then our follow-up with the answer to that is going to have to do with how bright a quasar would be if we put it in our galaxy.
Yikes.
How bright would it look if you put it in a little ball and put it 10 parsecs away?
Packaged it up and plopped it in our galaxy.
Yeah. So that's what we'll come
give
back
Brendan
to that,
some more nightmare fuel.
Yeah. But Tracy, what is new with Europa Clipper?
There's actually a lot of really new, exciting stuff with Europa Clipper. So right now, I think we're exactly 2 years out from the launch window of the mission. It'll be awesome.
So Europa Clipper is going to Jupiter and will be orbiting Jupiter, but studying Europa.
That's right. It's going to make something like close to 50 flybys of Europa as it orbits Jupiter. Basically, every couple of weeks, it'll do a flyby of Europa, and then it'll get way outside of Europa's orbit so that the radiation environment is less intense, because Jupiter's magnetic field causes a lot of radiation, really intense radiation, and all of the instruments would break down too fast if we kind of stayed in orbit within that magnetic field, within that radiation environment.
That answers the dumb question I had about why not just orbit Europa. Because I guess
that's the answer. So we go way out. It's the same thing that kind of Juno is doing right now too, where Juno gets way out and then comes in, does its observations real close to Jupiter, and then scoots right on out of there.
And Juno just recently did a flyby of Europa.
It did, and it's the first data we have of Europa since the Galileo mission, so since the 1990s.
Really amazing pictures. I mean, really beautiful stuff.
And there's going to be all sorts of cool instrument data, right? Because all of the instruments were on, not just the imagers. So they're going to get all sorts of particle and fields information. Ooh, it's going to be so exciting.
Are on the Juno mission. It's let out of Southwest Research Institute. So there's a lot of people that are giddy and not really sharing what they're giddy about. But there's, I think, a lot of cool papers coming out, and They've been
Let,
vague with
let,
me about what.
let me ask you a question. If one of our listeners happened to be like visiting Southwest Research Institute, what would be the signs that they would look for to see giddiness in your colleagues there at SWRI? What would that look like? How is it manifested?
Frantic typing for the most part.
Frantic typing, frantic typing.
Yep.
So are any of these
Going
results?
by and saying, "What are you doing?" And they're like, "Oh, I think we got some cool stuff, but we'll see. Let's see what the paper looks like." And that's sort of.
And then they're like,
Will these results be? Is there anything that could be useful to Europa Clipper in this time frame before launch?
Absolutely. So, and that was, I think, part of one of the reasons NASA wanted to extend the mission so that they could do these flybys. One of the big ones for us, at least, I work on the UV instrument, the ultraviolet instrument that will be on Europa Clipper. And one of the concerns we have is that radiation environment. So that causes a lot of noise in our data. So it'll be harder to pull out the actual signal from Europa. But the flyby actually is giving us those direct measurements of how bad is the radiation environment when you're actually next to Europa. And more interestingly, there's indications that if you're sort of in the wake of Europa, that radiation environment signal might drop down. So we might have better data than anticipated or worse data than anticipated. And this is the type of stuff that those measurements are going to help us with already.
Yeah, I was hearing some crazy things that like maybe you get like a huge drop in radiation close to Europa, which is bonkers.
Yeah, well, when all these giddy fingers finish writing their papers, we'll
I love the image there. So Europa Clipper, you says about 2 years away. How long does it take to get to Jupiter?
we are going to do an Earth and a Mars flyby gravity assist. So it will get there in 2030.
Okay, so 2024 launch, 2030 arrival. A Mars gravity assist is not something you hear very often
No.
because it's a pretty puny planet.
Yeah.
So
Aw.
yeah, it is. That's like getting, it's like getting a Ceres gravity assist, or something. It's like we're doing an Earth, Venus, Vesta gravity assist trajectory.
Poor
So
Mars.
you get out there at a 2030, and if you said 50 flybys every couple of weeks, so it sounds like a 2-year nominal mission.
Yeah, something like close to 3, I think.
Okay. And what sorts of things is your instrument, the one you're working on, going to be looking for in particular?
Yeah, so the ultraviolet instrument, which I did want to add in terms of updates about Europa Clipper, is already on board. It's been integrated into the spacecraft.
Ooh,
So about
That's
that's
awesome.
exciting.
Yeah, so about half of the instruments have been integrated onto the spacecraft now, and you can actually watch it live. If you go to JPL's website, you can just see the big clean room where they're putting all the instruments on the spacecraft, which is
That was going to be my next question. So it's in the JPL high bay?
Yep.
Awesome.
Yeah. And so the UV
Cool.
instrument was the first one, I will also say, to be integrated onto the spacecraft. We delivered it earlier this year. And the main sort of fun name that it has is the Plume Hunter. And that's because the first possible detection of plumes, or basically water volcanoes on Europa, came from UV observations using the Hubble Space Telescope. And so one of the
detections in air brackets, right?
I didn't put air brackets, but I said potential. But there are air brackets around them. And so that's one of the main goals, but really also just to study the atmosphere and how it changes, and especially how it changes in response to that intense magnetic field of Jupiter, which sort of wobbles around. And so it causes a lot of the atmospheric emissions to kind of change its location on Europa's atmosphere. And yeah, so those are the primary goals, really, to understand the atmosphere and to look for these possible plumes.
So what's your personal bet? Nobody's going to hold you to this. Your bosses aren't going to hear any of this. Nobody
They're totally
listens
going
to
to hear
this
it.
show, so you don't need to worry about it at all.
We have lots of faithful listeners.
Do you think that you will detect? Now, you worked with me when you were a grad student on looking at UV data and looking for some faint, funky, little weird signatures, not plume absorptions, but things along those lines. And we actually, our instrument on Cassini saw absorption from plumes from Enceladus. And so you know what that looks like. You know what the hunt for plumes from an icy moon looks like with a UV instrument. Do you think you're going to see them at Europa with Europa Clipper with your instrument?
So if they're there, I think the difference is that at Saturn, we didn't have that intense magnetic field to cause the emissions from the plumes the way we will with Jupiter at Europa. And so what caused the actual plume detection wasn't sort of this absorption of a background star or background Jupiter, which actually is one way that they have done it since the original detection. But the first way it was detected was by looking at emissions of hydrogen and oxygen at the exact right ratio to indicate that it had once been a water molecule that had been basically blown up from the radiation environment. And so we'll do one of the cool things that Europa Clipper will do is
a long walkabout.
Just too many caveats here.
It'll scan across Europa's surface. It'll scan across the whole thing, and we'll look for those kinds of emissions.
Yeah, so I know you're going to look for them. I know you're going to look for them.
I think because we're doing it as missions, it's a little bit easier to spot than if we were just looking for the right timing of a star to go right behind an unknown location.
That's fine. That's fine. No, I didn't mean to say, are you only going to see them in occultation? So
He's asking, do you think there are plumes there?
I appreciate the clarification that you can see them in multiple ways with this instrument, which is awesome. And I think emission is a really, a great way to see it too. Are you going to see them?
I think yes.
All right.
You think yes? All right.
You're on the record.
Heard it here.
Tracy's putting her money in the pool. Yes, they will see plumes. How about the rest of the team? What do you think, Jim?
Yes.
Ooh. All right. Hannah's nodding.
United.
Astroquarks United for plumes on Europa. Addie, what do you think?
I think there will be emissions. I don't know if there'll be plumes in the same way.
Okay. Hannah, you think maybe they'll see something, but kind of maybe ambiguous or
the plumes on Enceladus, right, are like these really distinct, really large plume features, right? And I think there might be like stuff coming up out of Europa in similar ways, but like we just don't have the same types of features where you have this giant crack where you're going to have the pressure and all that stuff that we know of, right? And so like I think that there might be like little cryovolcanic or like smaller regions where there's fissures or something. And
so maybe more like a diffuse, maybe sort of a diffuse atmosphere kind of high water molecules out there or something like that.
I'm Hannah, just making this up right now.
Yeah.
I'm taking the stance of I don't know enough about this to have an opinion that matters.
Boo!
So I'm not putting my money on something that I don't know enough about.
The beautiful thing about science is none of our opinions matter. Our opinions don't matter.
I don't even have an
anyway.
opinion because I don't really know enough to. I'd just be taking a stab in the dark, like all of my answers to all of my trivia questions.
None of our answers swayed you.
If anyone, probably you, Addie. Yeah.
Yeah.
So, yeah.
I think I wasn't thinking along those lines, but I actually do like your answer, Addie. That it's not going to be these, sort of really old faithful style geysers of things coming out, but something maybe a little bit more diffuse and global.
It's
or something like that.
It's not the size of the geyser, it's how you use it.
Okay. Well, on that note, Jim, let's talk about black holes.
All right.
Yeah.
Well, actually, yeah. So I was thinking back to 300 episodes. I have actually not been on all 300, of course, because obviously, as we said, Tracy was the original Top Quark. I don't know how many episodes you were on, Tracy. 100, 50, 70? I don't know.
We looked back at one point. I think it was in the dozens. But I wasn't even an original.
Tracy wasn't on the very first. The very first, like 3 episodes were me, Addie,
that don't exist anymore,
and Ashley Kehoe, and they have been expunged from reality. Not because of Ashley, but because of my horrible production.
But they still count, right? Those are still episodes 1, 2, and 3, or whatever.
Those are still episodes 1, 2, and 3.
Okay, and then you had some dozens of episodes with Tracy, and then of course she went on to greener pastures, and then I took over. But it's been a lot of years since I've been there.
You've been stuck here in the
It's much more
One is-
deserty out here than it was in Orlando.
That's true.
Oh, that's true.
Browner pastures, but greener because you're making way, way, way more money. Than
Making more green.
But yeah, so I was just thinking. I mean, as our passionate listeners know, I haven't really been on many episodes recently because I have a new baby and I'm here at home, and I'll be back in
Yay.
months. But I was thinking about all the fun things we've talked about for 300 episodes, and I was trying to decide for myself what was the coolest. And I think the two coolest things that we have talked about from my perspective over these few hundred episodes are, one was the images of the black hole, but I'm not going to talk anymore about that because we've talked about that ad nauseum. And two is looking at black hole collisions with gravitational waves. And more broadly, just talking about gravitational waves and the first detections of gravitational waves. So instead of I know maybe on the next episode I'm on, Josh, we can get into holographs of whether our universe is real or not. Because I know
I'm just gonna keep punting that one, Josh.
I know it's a really cool. That's a really cool thing. Josh, I know Josh wants to talk about it. I was just going to mention LIGO and gravitational waves because I think if I had to pick one thing that was the coolest thing that we've talked about in these episodes, I think that is it. Mostly because it's a new way of getting information in astronomy. We've been so. I mean, you've heard all the things that all of you guys have talked about. It's all light, gathering light, using light of all the different wavelengths, which is awesome, of course. And
Sure.
That's way better than just in the very old days when it was just visible light. But there's other things in the universe out there besides light that can convey information, and gravitational waves are one of them. And we have not had the ability to say, to detect those until our lifetimes, not just our lifetimes, but the last decade or so. And I think
Walkabout's lifetime.
I know that's truly an amazing thing. And I remember that first detection of two black holes colliding that LIGO, which was almost as soon as they turned LIGO on, right? In the first month or whatever, or weeks, they found that.
Sort of like their commissioning phase or something like that.
They weren't even really serious about the science yet, but bam, there was this big loud. Well, since then, there's been something like 90 detections of gravitational waves.
What?
By LIGO. But you know what? We haven't talked about them recently, and the reason is LIGO is down right now. It's not busted or anything, like, unfortunately, Arecibo and whatnot, but it is being upgraded, and it takes quite a while to do that. So I think mid-2023, it's going to be turned back on, the next run for LIGO. And, of course, now LIGO is being joined by Virgo, which is the same kind of instrument, but in Europe, and by... And I forget the name of it. It starts with a K. There's a one in Japan now as well, Conga or something like that. In any event,
COGRA.
Okay, so
it's an acronym.
With these, and of course LIGO is 2 observatories. So this is like 4 observatories that we have. We're going to see amazing things starting in 2023, and of course this is just the very beginning as we get better and better detectors and space-based ones and all these other things. So I think this is the dawn of new astronomy. That was the coolest thing in 300 episodes for me.
Is there? Yeah. So when does that come online again?
Like I said, mid-2023. I think that they had planned on December 22, and turns out every time they plan on. I mean, this is true for all of these big instruments. You saw what happened to James Webb and whatnot, obviously, but JWST. But I think March 2023 coming back online.
Okay.
March 2023.
When are we going to get another new result about black holes from the Event Horizon Telescope?
Oh, that should
never.
Anytime. We still have not. Yeah, anytime. Well,
anytime. Okay. What do you mean? Never. Aren't they done?
No, I don't think they're
really.
Done. No, they're not done. When I say anytime, I don't mean anytime. I don't know. The answer is I have no idea, but they're not done. That was cool enough. They got so much press for that, and that was so awesome that now, of course, the 2 targets that they've taken pictures of, right, are the 2 that were the only obvious ones to take pictures of, the 2 biggest black holes in our sky. But they're certainly not the only ones that you could conceivably mess with. And so
there was a result about a blazar from the Event Horizon Telescope in August of this year that we didn't even talk about.
And a blazar is a particularly bright quasar, which brings
it's a really shiny jacket.
As you say, it's a quasar with a nice coat.
It's a blazar. It's a double-breasted blazar.
Oh,
That's what I'm gonna be for Halloween. We're recording this shortly before Halloween, and I'm gonna go as a blazar, a double-breasted blazar.
That's awesome.
I love it. Holding you to that.
Okay, your quasar trivia. The first part is, what's the distance to the nearest quasar? Shout it out.
6 billion light years.
6 billion,
5
says Jim
billion.
Cooney. 5 billion, says
1 billion.
Rob Ford.
Price is right.
500
1
million.
Sorry, how much?
Oh.
Hannah?
500 million.
Once again, having no idea what she is talking about, Hannah Sargent wins the trivia. 581.
She's back.
Both with regular rules and with Price of Right rules. 581 million light years, give or take.
Wow.
Can I
margin
retire
of
on that?
error. It's Markarian 231 in the constellation Ursa Major. Okay, now bear with me, please. As you know, this wouldn't be an episode of Walkabout the Galaxy, let alone the 300th episode, without an incredibly complicated follow-on to the trivia.
Sure.
For this follow-on, I have to remind our listeners about apparent and absolute magnitudes. Apparent magnitude is how bright something looks, and absolute magnitude is how bright it would be if you put everything at a common distance. And that common distance for planetary things, it's the distance between the Earth and the Sun. But for non-planetary things like stars and galaxies and quasars and blazars, it's 32.6 light years, 10 parsecs away. So that's a lot of the stars you see in the night sky, the dimmer are in the sort of tens of light years away from the Sun. So the question is, I'm going to give you comparisons to the Sun. The Sun's apparent magnitude, the Sun is the brightest thing in the sky, we can agree? Mm-hmm. I'm not hearing any dissension to that
not right now,
proposition. But the brightest thing in the sky is the Sun, and it has an apparent magnitude of minus 26.8. And the more negative the number, the brighter the thing is, because astronomers, right?
Because astronomers.
So that's crazy, crazy bright, minus 26.8. If you put the Sun out at that 10 parsec distance, its magnitude would be 4.8. Okay, so it would be pretty dim. You know, in any kind of city, you probably wouldn't be able to make that out with the naked eye.
Sure.
You know, but you could see it with binoculars, or if you were in a dark sky setting, you could see the Sun if it were 10 parsecs away.
Oh, I was going to make a mean joke, but now it's ruined.
So for
continue.
The mathematically oriented in the audience is that this magnitude scale is crazy. It's a logarithmic scale. It is
crazy.
So even that was like 30 magnitudes different. That doesn't mean it's 30 times dimmer. It means it's like 2.5 something to the 30th power times dimmer.
That's right.
Magnitude difference is a factor of 2.5 something.
It's 1 trillion times fainter out there. 10 to the 12 times fainter. 10 to the 30 over 2.5 times fainter. So the moon, just to give you another reference point, the Sun's apparent magnitude is minus 26.8. The moon's apparent magnitude, and the moon we know is a lot dimmer than the Sun. It's reflecting sunlight that's closer, minus 12.7. So your question finally, what would be the brightness of the brightest quasar, which is a quasar called 3C273? That's the brightest apparent quasar. How bright would it be if it were 10 parsecs away? Okay, I'll give you a hint. Its apparent magnitude is 12.8. So that's how bright it actually is, where it is, way the hell far away from us. If you moved it to 10 parsecs away from the Earth, what would be the magnitude of that quasar?
Minus 42.
Minus 42. I like you going for it.
Minus 100.
Minus 100. Really going for it.
Minus 10.
Minus 10. Jim is actually trying to figure this out.
I was going to
You can tell.
You can see the
He's
wheels
actually
turning, calculating,
he's doing some
calculating.
mental math here.
I won't bother calculating. I'll just get minus 53.
Minus 53, and I think once again the person who
Hannah's
knows
gonna
the
get it.
least wins, although still wildly off from the correct answer, which is minus 26.7, or basically as bright as the sun.
Wow.
So if
Oh,
you
cool.
took that quasar, the brightest quasar in the sky, and moved it to the
Wow, that's
standard
so bright.
astronomical distance, it would be as bright as the sun actually is in our sky.
That's
Minus
obscene.
26.7, so just
That's
about the
fun.
same brightness as the sun. Now, the actually most intrinsically bright quasar is 5 magnitudes brighter than that. And if we put it at that distance, it would be then minus 32 magnitudes, or 150 times brighter than the sun. Happy to know. You're all happy
That's
to know.
exciting.
Last,
Yeah, that's crazy though.
last follow-up, if you took that brightest quasar, the brightest one that we see in the sky, and put it at the center of the Milky Way, how bright do you think it would be, like compared to moon, sun, all this other stuff? You know that if it's close by, it would be as bright as the sun. How bright would it be if it were at the center of the Milky Way? And we'll take your answers as we're joined by mini quark Riley Karina Charm Quark. Jim, what do you think? Do some mental math. I want you to get this one right. If we take the quasar, the brightest quasar in the sky, and put it at the center of the Milky Way, how bright is it?
It's full moon.
I like that answer so much that I'm not going to make everybody else answer. It'd be almost as bright as the
Yay.
full moon.
Nice job,
Oh,
Jim.
cool.
Well done, Jim.
Yay. Thanks for saving us too.
While it may have felt like 300 episodes, it was just the 300th episode of Walkabout the Galaxy. Give us 5 stars, and we'll give you 300 more episodes. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere by emailing wtg@ucf.edu. Our theme music was composed by Richard Jerusik. Thanks to our listeners on planet Earth and around Proxima Centauri, 4 light years away. Note to Proximans, when you hear this, we'll have already recorded our 400th episode.
Aw.
Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
I'm Jim Cooney.
I'm Tracy Becker.
And I'm Hannah Sargent.
We're the Astroquarks, signing off until the next episode of Walkabout the Galaxy.